Hi guys, this video I'll be talking about spanning tree protocol and try to explain it in simple terms and just be using a couple of topologies to explain it better so that it's easier to understand. And as you should know, the spanning tree protocol is used for loop prevention in the layer 2 network. So here we have 3 switches. It's a very small topology. So I've got the same topology here in paint. I'll be using the legend here. The designated ports will have a couple of arrows. Root ports, a single one, and non-designated port will just have a cross. So I just want to go through the working of spanning tree protocol, what happens first, and how the spanning tree converges. And once we've done that, then we'll move on to the actual simulation and see if the result matches with the discussion that I'll do here in this topology in paint. So the first thing that spanning tree does is the root bridge election. So the other thing I'll do also is that when once I've shown you guys how spanning tree works in both topologies, then I'll be changing I'll basically show you guys how to manipulate the root bridge election by selecting the priority, changing the priority of the root of the switches. So you can force, by changing the priority, you can select switch 1, switch 2, or switch 3. Any of those switches to become the root bridge, and you can have a primary one, you can have a backup one as well, a secondary. That will act as a backup switch. So in case if the primary one fails, the secondary will take over as the root bridge. So just starting with how the spanning tree protocol works, the different stages that it goes through. The first thing is the root bridge election. So the priority in spanning tree protocol is the default priority is 32768 plus the system ID extension. So which is just the VLAN number. So in this video, I'll just be working with VLAN 1. So the system ID extension will just become 1 in this case. So so if the priority is default on all 3, the second thing the spanning tree protocol will look at is the MAC addresses. So if the switch 1 has the lower MAC address than switch 2 and switch 3, switch 1 will be elected as the root bridge. So the root bridge will have all its ports in forwarding state, and there'll be designated ports. So let's start with that. We'll have both Ethernet 00 and Ethernet 01 designated ports in forwarding state on switch 1, the root bridge. So let's just do that now. Right, so we have the 2 ports, Ethernet 00 and Ethernet 01 of switch 1 as designated ports, both in forwarding state. The next thing the spanning tree does is on the non-root bridges, i.e. switch 2 and switch 3, the root port will be selected on each bridge. So the root port will be the primary port facing the root, i.e. the port with the lowest cost to reach the root bridge. If there's a tie in the port cost, the switch will look at the lowest port priority of the upstream neighbor. So on switch 2 and switch 3, both Ethernet 00 and Ethernet 01 will have cost of 100. So then it's going to look at the port priority of the upstream neighbor. So switch 2 will look at the port priority of switch 1 and switch 3. So switch 1 will win, and switch 3 will do the same. We'll look at the port priority on switch 2 for this interface, and we'll look at the port priority of switch 1 as well for Ethernet 00. So in both cases, Ethernet 00 on both switches will win, because the port priority of the upstream neighbor on switch 1 will be lower than of switch 2 and switch 3. So these two will become the root ports. So let's just do the arrows on these just to indicate them as root ports. Right, so we have the root bridge with both its ports in designated ports. We have also the root ports now on switch 2 and switch 3. So the root ports and the designated ports are all in porting state. So now the next thing that the spanning tree will do is select the designated ports on the root non-root bridges. So i.e. it needs to choose a designated port on this link between switch 2 and switch 3. The designated port, there has to be one designated port per segment. So in this case, we have a designated port of the root bridge on both Ethernet 0001. The other end are the root ports, so we can't have designated ports on both ends of a link. So in this case, on Ethernet 01 between switch 2 and switch 3, the designated port the spanning tree looks at the accumulated cost to the root bridge. So on both switch 2 and switch 3, it will be there will be a tie. So if the links are 10 meg, the spanning tree will assign a cost of 100. So it's going to have a cost of 100 for switch 2 and on switch 3 as well for Ethernet 01. So if there's a tie in the accumulated cost, then it's going to look at the lower switch ID of the bridge. So switch 2 will win against switch 3. It has a lower spanning tree switch ID than switch 3. So Ethernet 01 on switch 2 will become the designated port. So we'll assign this. There we are. So this is the designated port on this link. And as we can only have one designated port per segment, and switch 3 already has a root port, Ethernet 00. So Ethernet 01 will now become the non-designated port. Right, so here we have the spanning tree has converged. So the root bridge was first selected based on its lower MAC address. Then the root ports were elected by the non-root bridges, Ethernet 00 on both switch 2 and switch 3. Both ports facing the root bridge. So lower cost, or you can say the upstream neighbor had a lower cost. So i.e. the lower port priority of the upstream neighbor. So in this case, obviously switch 1 wins. So and then the selection of the designated port. Again, the accumulated cost was the same on both switch 2 and switch 3. So switch 2 won because it has a lower spanning tree switch ID as opposed to switch 3. And finally, the non-designated port. I mean, all the ports that are not designated ports and not root ports are then become non-designated ports, are put in blocking state. So here we have. Now let's just check on the simulation and see if the result matches, just to make sure that we got it right. So we have the same topology in the Eve simulation software. So let's go on switch 1. So just working with VLAN 1, just to keep it simple. So show spanning tree. I mean, if you had more than one VLAN, you will basically, if you want to check it per instance, you can do show spanning tree, and whichever VLAN you want to check. So in this case, we just have the one VLAN, so show spanning tree. We don't even need to specify the VLAN. So this switch 1 would have been elected as the root bridge. Why would it have been elected as a root bridge? If you look at the MAC address now, so it has a MAC address of the last AA.BB.CC00.1000, and if we compare that with switch 2 and switch 3, you can see that switch 2 has a higher MAC address, so .2000 as opposed to .1000 on the root, and switch 3 would have .3000. So we have switch 1 elected as a root bridge. The port priority is 32769, so which is the default 32768 plus the system ID extension, which is the VLAN number 1. So 32768 plus 1, 32769. So the port priority would have been the same on the 3 switches, 32769. So it would have been elected as a root bridge based on a lower MAC address. So as I said in the on the topology here, that the root bridge would have all its ports elected as designated ports. So this being confirmed here, we have both ports Ethernet 00 and Ethernet 01 of the root bridge as designated. So this confirms what we discussed earlier. So now moving on to switch 2. Ethernet 00 is elected as a root port, same as what we discussed here in Paint, that Ethernet 00 is a root port on both switch 2 and switch 3. So switch 2 having elected Ethernet 00 as root port, and Ethernet 01 became the designated port. It won the election between switch 2 and switch 3 regarding the designated port election. So the actual simulation confirms that, and switch 3 has the Ethernet 00 port as root and Ethernet 01 as the blocking state, just as I crossed it out here. So now if we just go through the show span tree output and just to see what the IOS is telling us. So the first thing that it tells us is the first section is the root bridge information, and then it tells you some information about the bridge, the switch itself. So it gives us the priority of the root bridge 32769, gives us the MAC address, and it tells us that this bridge is the root, and it tells us the hello time, the default. So the default is 2 seconds, the max stage timer is 20 seconds, and the forward delay is 15 seconds. I'll talk a bit about the 3 hello time, max stage, the 3 timers here in a minute. And then it tells us it gives us the information about the bridge itself, the switch. So in this case, switch 1. So the priority, this bridge is the root bridge. So the same information we'll have here. Priority is 32769. Address is the same here. Same the hello time, max age and forward delay, and the aging time of the switch. And then the information about the interfaces. On switch 2, this information is about the root bridge information. So switch 1. So the priority of switch 1, the address, the MAC address, the cost is 100. So the port Ethernet 00. So it's telling us that the cost to reach. So for switch 2, the cost to reach the root bridge is 100, and Ethernet 00 is the root port. So it's telling us here that the root port is Ethernet 00, and the cost is 100 to reach the root bridge switch 1. And we have the 3 timers here, the default, and now the information about the switch 2 itself, the local switch. The priority is the same as a root bridge. The address is higher than switch 1. The timers we have same as switch 1, and then it's telling us the status of the two ports. Ethernet 00 is the root port, Ethernet 01 is designated, and finally the same thing on switch 3 as well. So this information about the root bridge, this one about this section is about the bridge itself, switch 3, and the two ports, root and alternate blocking state. So Ethernet 00 is forwarding, Ethernet 01 is blocking. So now just talk a bit about the timers. So hello time, the max age, and forward delay. So the hello time is the interval, i.e. 2 seconds, the default, in which the BPDUs are being sent by the root bridge designated ports. So what happens is that only the root bridge will be forwarding the BPDU's bridge protocol data units via its designated ports. So Ethernet 00 and 01 are both generating BPDUs every 2 seconds, which is the default. On the non-root bridges, the BPDUs are received by the root ports and the non-designated ports, and are relayed or forwarded by the designated ports of the non-root bridges. So in this case, switch 2. So the switch 1, the BPDUs generated by switch 1 are received by the root ports Ethernet 00 and Ethernet 00 on switch 2 and 3, and by the non-designated port on switch 3 Ethernet 01, and are forwarded and or relayed by the designated port Ethernet 01 on switch 2 every 2 seconds. The second timer we have is the max age timer, 20 seconds. So the max age timer is to detect sort of a topology change in layer 2. So in this case, the default is 20 seconds. So what's happening is that every time a BPDU is sent by the root bridge, so the ports that are receiving these BPDUs, i.e. the root ports and the non-designated ports, so they check in that as long as the BPDUs are equal and or higher than the ones they have stored in their database, the max age timer will be reset. So every 2 seconds they receive a new BPDU, and if it's equal to the previous one received, or if it's better than the previous one received by the ports, the max age timer will be reset. But if the BPDU has a lower value than the one previously stored or previously received, then the max age timer will not be reset. So the timer will count to the value of 20 seconds. The default in this case is 20 seconds. So we have max age timer of 20 seconds. So what happens is that the BPDU is if the BPDU received is lower, then the max age timer is not resetting and is counting up to 20 seconds. So the two scenarios, let's study the two scenarios where the max age timer will not be reset and will reach its maximum of 20 seconds. So the first case, we could have let's say spanning corrupted software. So in this case, switch 2 stops forwarding the BPDUs received by switch 1, and so the non-designated port on switch 3 Ethernet 01 is not receiving any more BPDUs from switch 2. So one thing is that these timers are port specific; they're not bridge specific. So even though Ethernet 00 on switch 3 is receiving the BPDUs from switch 1, if Ethernet 01 stops receiving BPDUs from switch 2, it will act individually. It will act separately to the port Ethernet 00. So it's port specific, not bridge specific. So Ethernet 01 for some reason is not sending any more BPDUs, and the non-designated port here. So the max age timer now is not going to reset after 2 seconds. So it will count up to the default value of 20 seconds. So what happens? Right. So like I was saying, guys. So the non-designated port is not receiving any more BPDUs from switch 2. The max age timer will count up to 20 seconds. The timer, that is the default. So default is 20 seconds. So once the max age timer reaches 20 seconds, the port from non-designated port will now become a designated port. So what's going to happen here is, let's cross this out. And now let's change this port and make it a designated port. Right, guys, so now you can see that we have 2 designated ports per segment. I mean, even though this we have a corruption of the software, so Ethernet 01 is not sending any BPDUs, but what's happening is that it's going to cause a loop. So we'll have a loop, and the spanning tree is basically not going to be doing its job, and we have no loop prevention, but that's just a corruption of the software. So the second scenario that we can discuss is let's just take this back out again and just cross it out again, make it back into a non-designated port. Right, the second scenario I want to discuss is that, let's say we have a link failure. So right, so the second scenario I want to discuss is the indirect link failure. So if we have the indirect link failure between switch 2 and switch 3, so we just remove this. There we go. Right, so Ethernet 00 is gone. So now switch 2 is not receiving any BPDUs. So in this case, what's going to happen is that it's not going to need to go through a max age timer, expiration of max age timer. It's not receiving any BPDUs, so it's just going to consider itself the root bridge. So switch 2 will just consider itself the root bridge, and will have its Ethernet 01 port as a designated port and in the forwarding state. So the non-designated port Ethernet 01 or switch 3 will start receiving the BPDUs now from switch 2, which are inferior to the ones that had received from previously from switch 1. So but I mean, like I said, I mean, these timers are port specific. So switch 3 is still receiving better BPDUs from switch 1 on Ethernet 00. But on Ethernet 01, now it's receiving worse, inferior BPDUs from switch 2. So the max age timer will not reset every 2 seconds now. So it'll basically, it's going to ignore the BPDUs, and the max age timer will keep on counting to its value of 20 seconds, the default value. And once it reaches the value, once it reaches 20 seconds, the port would now move from non-designated into designated. So it'll become a designated port, and we'll start forwarding as well. So in this case, we're just going to change the direction because the BPDUs are received on Ethernet 00 here, so it's going to, there we go. So this port is now designated port as well. So now what's happening is that Ethernet 00 on switch 3 is receiving better BPDUs from switch 1 than the the Ethernet 01 port was receiving from switch 2. So switch 2 was sending inferior BPDUs. So switch Ethernet 01 transitions from non-designated and becomes a designated port. So like I said earlier, we can only have one designated port per segment. So now switch 2 is receiving better BPDUs from switch 1 on Ethernet 01 from switch 3. So this port will now transition and it will become a root port. So there we have it, guys. So we have switch 2 has just one root port now facing switch 3. Switch 3 has Ethernet 01. This one is the designated port. Ethernet 00. So switch 1 now is basically the original topology has returned. We have the same scenario now. So that we have the indirect link failure, Ethernet 00. But switch 1 has now, so spanning tree has converged. Switch 1 is now still the root bridge. So it's only one port is in designated is a designated port in forwarding state. This port is the root port facing switch 1. Switch 3 Ethernet 01 becomes a designated port, and Ethernet 01 on switch 2 becomes the root port, and the spanning tree has converged, and we won't have any loops. So the second topology I want to discuss is a big wall. We have 4 switches, and we have 2 links between switches, Ethernet 0001, and we have 4 links per switch basically. So a slightly bigger topology. So hopefully that'll explain it a bit better. Spanning tree. So we have 2 topologies. Probably explain it better than just having one topology. So same scenario as the previous topology. We'll have the default priority of 32769, 32768 plus the system ID extension of VLAN1, which is just the one. So switch 1 will have a lower MAC address than switch 2, switch 3, and switch 4. So switch 1 will become the root bridge, and all its ports will become designated ports. And in forwarding state. Guys, should have maybe had more space here, but there you go. So the 4 ports in designated. Fine, easy one. Right, so the root port has the 4 ports in forwarding state, designated ports. The second thing that a spanning tree will do now is the root port selection of the non-root bridges, i.e. switch 2, switch 3, and switch 4. Right, so starting with switch 2, the first thing spanning tree will look at is the port cost. So both ports, Ethernet 00 and Ethernet 01, will have the port cost of 100. So there's a tie here. So the second thing it's going to look at is the lower port priority of the upstream neighbor. So in this case, switch 1. So port priority for Ethernet 00 and Ethernet 01. So the port priority of Ethernet 00 on switch 1 is going to be lower than that of 01. So Ethernet 00 will be elected as the root port. Let's designated as the root port. So that's switch 2. Switch 3, same thing. We have these two ports that have the same cost. So there's a tie in the port cost. So it's going to look at the lower port priority of the upstream neighbor. So Ethernet 0100 will win for on switch 1 as opposed to Ethernet 01 on switch 1. So Ethernet 00 will become the root port. And finally on switch 4, we have all the 4 ports will have the same cost. So there will be a tie. So the lower port priority of the upstream neighbor, switch 2 and switch 3. So switch 2 will win. And between Ethernet 00 and Ethernet 01, Ethernet 00 will win. So Ethernet 00 will become the root port. So we have, so the first thing was the root bridge election. Switch 1 became the root bridge. Then the second thing we had the root port selection on the non-root bridges. So switch 2, switch 3, and switch 4. That has been done as well. So the third thing the spanning tree will do now is the designated port selection. So the first thing that the spanning tree will look at is the lower accumulated cost to the root bridge. So that's the first thing, and if there's a tie, it's going to look at the lower spanning tree switch ID of the switch, and that'll become the designated port. And one thing to remember, guys, we can only have one designated port per segment. So in this case, we have the designated port here, and we have the root port. Even though both are in forwarding state, but there's only one designated port per segment. So we already have one designated port here. We can't have a designated port on this end of the segment. So this one will automatically become a block port, but we'll get to that in a minute. Let's just go ahead and select the designated ports on the links where we don't have any designated port selected as yet. So let's start with this link. So the accumulated cost. So the first thing will be the accumulated cost. So switch 4 will have accumulated cost of 100 plus 100, 200 to reach the bridge. Switch 2 will have the accumulated cost of just 100 to reach the root bridge. So switch 2 will win straight away. It doesn't even need to look at the lower spanning tree switch ID. I mean, even though switch 2 will win on that front as well, but it doesn't really need to get to that. So switch 2 will win the election on that, and it will have the this port will become designated port. And switch 4 will automatically put this in blocking state. Right, guys, so in this case, let's not forget this link as well. This link, we have the root port. We need to have a designated port on this link as well. So Ethernet 02 will become the designated port on switch 2. So we have these two segments taken care of. We have this segment taken care of. Let's just take care of this one as well. So we have the designated port already on this link. So this Ethernet 01 port on switch 2 will become the non-designated port, and we put in blocking state. So we can only have one designated port per segment. Same thing here. We have the designated port here. This one has to become a non-designated port. Right, guys. So these two links, and these two links, so all 6 links have been taken care of. So we just have these two links left now. So both switches have already elected their root ports. So we're gonna have 2 designated ports on these 2 links, and 2 non-designated ports. So how will the spanning tree work? So the first thing it's going to look at is the accumulated cost to reach the root bridge. So switch 3 will have a lower accumulated cost. It just gonna needs the accumulated cost is 100 to reach the root bridge, whereas switch 4 has an accumulated cost of 200. So both these ports will become the designated ports. It doesn't need to look at the lowest switch ID. The accumulated cost was enough. So we make these two ports designated ports. And as we can only have one designated port per segment, these two ports will become non-designated port and will put in blocking state. Cool, here we are, guys. So now let's have a look at the on the simulation itself, and just to double check our assessment of the workings of the spanning tree. So hopefully we should be all correct, but let's just double check that. Right, so we have the topology here in Eve simulation. So the same topology: switch 1, switch 2, switch 3, switch 4. The same 4 links per switch. So let's just double check and compare it to what the workings that we did on the topology here. So we compare it. Let's start with switch 1. So switch 1 was elected as the root bridge, and all its 4 ports are in forwarding state, designated ports. So that's fine. Alright, let's move on to switch 2. Ethernet 00 has been elected as a root port. Yep, Ethernet 00 is a root port. Ethernet 01 is in blocking state. Ethernet 01 is in blocking state, and Ethernet 02 and 03 are both in forwarding state. Ethernet 02 and 03 are both in forwarding state, so that's fine. Moving on to switch 3. So Ethernet 00 is a root port, and Ethernet 01 is blocking state. So Ethernet 00 is the root port, and Ethernet 01 is in blocking state, and both Ethernet 02 and 03 should be the designated ports. So here we have Ethernet 02 and 03 are both designated ports and in forwarding states. And finally, looking at switch 4. So switch 4 should have Ethernet 00 as a root port, and all the other ports should be in blocking state. So yes, we do have Ethernet 00 as a root port, and all the others are in blocking state. So just to explain spanning tree, I think it's a good practice. It's good practice to actually have a topology and then work out how the spanning tree will converge, and then test it with the actual simulation in Eve on actual devices themselves, just to see whether your the way you had had it converged, whether it matches with the actual simulation. So a couple of things I forgot to mention as well. So I talked about the hello time, the max age time. The forward delay is just the time spent in listening and learning states. The aging time is the aging time of the MAC address table. So when a switch sends the MAC address, so if the aging time is 300, the switch will put it in this MAC address table for 300 seconds. So as long as that switch sends another frame in this period, it will put that MAC address back in the address table. But if it doesn't receive any more frames from that switch for the duration of 300 seconds, that MAC address will be aged out, and it'll be removed from the MAC address table. So that's the aging time. So as I also explained earlier, that this section is about the root bridge, and this section is about the switch itself, the local switch. So the priority of the root bridge, the address of the root bridge, the cost. Just to explain this a bit more, so the root port for switch 4 is Ethernet 00. The root port is Ethernet 00, and the cost to reach the root bridge is 200. So the cost to reach the root bridge is 200, 100 plus 100, 200. And these are the timers that I've already discussed. So this is the local bridge now. So the priority is the default plus the system ID extension, which is the VLAN number, the MAC address, 4000, .4000, lower than the MAC address of the root bridge. The hello timer, the max age timer, the forward delay timer, and the aging time, and then the 4 interfaces. So it just tells us about the interface. So I mean, I did mention the couple of things as well. I mentioned the cost of the interface, and I mentioned I also talked about the priority of the upstream neighbor. So in this case, switch 4, so the upstream neighbor for these two ports, Ethernet 00 and 01, will be switch 2, and for 02 and 03 will be switch 3. So when there's a tie in the cost, like I mentioned, it's looking at the priority of the upstream neighbor. So Ethernet 00 will have 1 because it has a lower priority of the upstream neighbor for Ethernet 00 compared to the other ports. So that's pretty much the explanatory explained. The other thing I wanted to talk about was how to then change. So at the moment we have switch 1 as the root bridge, and so this is a primary root bridge. We didn't have any backup root bridge, so we don't have a secondary root bridge. So we want to configure switch 4 as a root bridge for VLAN 1, and we also want to have a backup root bridge. So if switch 4 goes down, we want to have switch 1 as the root bridge. So we want switch 1 to take over the role of the root bridge in case switch 4 goes down. So let's go and configure this now. So we just have VLAN 1, the default VLAN. Haven't configured any more VLANs, so let's just configure that. So we're going to have explanatory VLAN 1, explanatory 0. Right, this will ensure switch 4 will become the root bridge. So if we do show span 3 now, we can see that the priority now is 1. Address is 4000. This bridge is the root, even though it has a higher MAC address than the MAC address of switch 1, which was .1000. And it's telling us in this section as well that this local bridge has a priority of 1. So priority set was 0 plus system ID extension 1, and all its ports are now in forwarding state. Designated forwarding. Well, they are blocking, but it hasn't, the quality hasn't converged at the moment, so we'll get to that in a minute. So in case switch 4 goes down, switch 1 should become the root bridge. Right, so we want to select switch 1 as the secondary route. So in case switch 4 goes down, switch 1 will take over the role as the root bridge. So let's just configure that. So property, so spanning tree, VLAN 1. So there's another way of configuring the primary and the secondary root bridge. You can just assign it the priority. So in this case, we can assign a priority of 4096, which will make it the secondary because the primary has a I set it as 0. Or you can also choose this command, root, and then we have the option of selecting as primary or secondary. So this one, we want to make switch 1 as a secondary route. So let's make it secondary. Let's save the config and let's go to switch 4 and save the config as well. So now, alright guys, so just want to go through this the same procedure that we went through with the same small the two topologies, but in this case now we have switch 4 as a root bridge, and if switch 4 fails, we have switch 1 as a root bridge. So in the previous example we had switch 1 as the root bridge. So we're just gonna go through the same, so that way you probably understand it, and it will just confirm our understanding. So switch 4 is the root bridge. All its ports will be designated port and will be in forwarding state. So let's do that. A bit wonky there, but never mind. So the 4 ports are in forwarding states, and they're all designated ports. So the first thing. Now the second thing will be the selection of the root ports by the non-root bridges. So switch 2, switch 1, and switch 3. So they'll be looking at the in this case they look at the port cost first, and if the cost is are the same, then it's going to look at the lower port priority of the upstream neighbor. So in this case, for switch 2, the cost will be the same for Ethernet 02 and 03. So it's going to look at the lower port priority of the upstream neighbor for switch, which will be switch 4. So Ethernet 02 will win. So Ethernet 02 should become the root port. Let's just select that as a root port. So as we can only have one designated port per segment, we have the one here. This one is root, so this one will be in a non-designated port, because we can't have a designated port here as well. So that's switch 2. Switch 3 will have all its ports will have the same cost. So they have the same cost. So the lower port priority of the upstream neighbor will be Ethernet 00. So this one will become the root port for switch 1, and for switch 3, these two ports have lower cost than Ethernet 0001. So for Ethernet 02 and 03, it's going to look at the lower port priority of switch 4 for the same ports. So Ethernet 02 will win. So this port becomes the root port. And this one, so this one is the root port. So we have now the root port selected for the non-root bridges. So the root bridge was selected. We enforced by assigning a priority of 0. So we enforce 0 switch ports to become the root bridge. All these ports are in designated ports. Then moving on to the root port selection for the non-root bridges. So switch 2 has Ethernet 02, switch 1 has Ethernet 00, switch 3 has Ethernet 002. So now we move on to spanning tree. We'll move on to the spanning tree designated port selection. So the first thing it will look at is the accumulated cost to reach the root bridge. If there's a tie, then it's going to look at the lower spanning tree switch ID of the switch. So let's start with switch 2. These two segments, these two interfaces are taken care of. So if you look on this segment, we have a root port here. So there has to be one designated port per segment. So Ethernet 00 will become the designated port. So let's just make it the designated port and in porting state. Right, and we also have a designated port here already. So this one has to be put into a blocking state. So this becomes a non-designated port. So these interfaces are taken care of. So we just have these three interfaces to take care of now. So which one will be elected as the designated port on this link? So switch 2 will have a lower accumulated cost to reach the root bridge. So Ethernet 01 will become the designated port. And since the designated port has been elected, the other end has to become the non-designated port. Right, so just have these two interfaces left now. So switch 3 will have a lower accumulated cost to reach the bridge as opposed to switch 1. So Ethernet 00 and 01 will win against the Ethernet 02 and 03 of switch 1. So these two will become the designated ports. And since we have the designated ports per segment, so these two will now become the non-designated ports and will be put into blocking state. Right guys, that's the spanning tree converged for this topology with switch 4 as the root bridge. So let's just double check now that this is actually what's happening. So switch 4 was the root bridge based on its lowest priority, and all its ports are designated ports and in the forwarding state. All are designated ports and in forwarding state. So let's look at switch 2. So we have root port is Ethernet 02. So looking at switch 2, we have Ethernet 02 as a root port. Ethernet 03 is a non-designated port. Yeah. And Ethernet 00 and 01 are both designated forwarding. Ethernet 00 and 01 are both designated ports. So switch 2 is as we worked out. So let's move on to switch 1. So switch 1 just has Ethernet 00 as root port, and all the others are non-designated ports. So yeah, that confirms it. Ethernet 00 is the root port, and all the other 01, 02, 03 are non-designated ports and in blocking state. So finally switch 2. The root port is Ethernet 02. Oh, sorry guys, I think we had switch 3 left. Switch 3 to take care of. Let's double check. So spanning tree. So on switch 3 we have Ethernet 02 as a root port, and 03 is a non-designated port. Ethernet 02 is the root port, Ethernet 03 is the non-designated port, and Ethernet 00 and 01 are both designated ports. And Ethernet 00 and 01 are both designated ports, which just confirms that the way we basically went through the workings of spanning tree protocol, how it would converge. So the actual simulation actually confirms our working. So hopefully that explains to you guys how the spanning tree works, how the root bridge is elected, how it converges, going through the different stages. And the second thing that also did was the root bridge election. I showed you guys two ways of one is to actually assign it a priority, the other is to actually just assign it using the command of primary and secondary. So primary will be the primary, secondary will take over the role of the primary bridge in case the primary went down. So that's it guys. Hopefully you guys would have a better understanding of the spanning tree protocol now, and any questions, comments, post them below and I'll answer as many as I can. Thanks.